Obtaining differential equations of magnetostatics and Ampere's law. Let's start with the expression from Biot-Savart when there is a current density J vector of x vector equation 6-71. From gradient cross B vector equals 1 over C gradient cross the integral from 2 of the fraction with numerator J of x prime and denominator the absolute value of x minus x prime d cubed x prime and gradient cross A equals gradient A minus gradient squared A. We have, see the equation shown, equals 1 over C gradient sign with over it the integral from 2 of J of x prime vector dot gradient prime, the fraction with numerator 1 and denominator the absolute value of x vector minus x prime vector times d cubed x prime plus 4 pi over C J vector of x vector equals 1 over C gradient sign with over it the integral from 2 of the fraction with numerator gradient sign with over it prime dot J of x prime vector and denominator the absolute value of x vector minus x prime vector d cubed x prime plus 4 pi over C J vector of x vector equals 4 pi over C J vector of x vector, since gradient dot J equals 0. So, equation 6-72.
Ampere's law is an integral form of the above. See the equation shown. See the equation shown. Thus, equation 6-73. Ampere's law can be employed advantageously, like Gauss's law, in highly symmetric situations.
Vector potential. Whenever you have gradient B vector equals 0, it is possible to make use of a vector potential B vector equals gradient cross A. Starting with the differential laws of magnetostatics. Equation 6-74. We can see that if J vector equals 0, we can have B vector equals negative gradient phi sub m, where phi sub m is a magnetic scalar potential and previous techniques from electrostatics come to bear. Let's now proceed with J vector is not equal to 0 and B vector equals gradient cross A. From B of x equals 1 over C gradient cross the integral from 2 of the fraction with numerator J of x prime vector, and denominator the absolute value of x vector minus x prime vector d cubed x prime, we get equation 6-75, where gradient cross gradient psi equals 0. Thus, a vector plus gradient psi makes no change in the magnetic flux density and is our first example of what is known as a gauge transformation. Given this freedom, it is possible to choose the gauge such that gradient.A equals 0 and using B vector equals gradient cross a vector. Equation 6-76, where each rectangular component of the vector potential satisfies the Poisson equation.
There is a surprising difference between cylindrically symmetric magnetostatic problems and corresponding cylindrically symmetric electrostatic problems. Associated Legendre polynomials appear together with ordinary Legendre polynomials. This can be traced to the vector character of the current and the vector potential, as opposed to the scalar properties of charge and electrostatic potential. Put another way, the electrostatic had completeness in terms of associated Legendre polynomial when the electric charge monopole was allowed. When there was no monopole in the magnetostatic case, completeness requiring a mixing of associated and ordinary Legendre polynomials isn't a surprise. Furthermore, the natural extension, via analyticity between the two Legendre polynomial solution families, associated and ordinary, to encompass both suggests an underlying construct consisting of a mixture of E and B 3D vector fields as some other construct. To be elaborated when seen together comprising an antisymmetric 4D tensor and the special relativity formulation of EM that follows. As with the moment expansion for electrostatics, the moment expansion for magnetostatics is given by the multipole expansion. The magnetic dipole moment being the lowest order term, there being no monopole, is then found to be equation 6-77. For a planar current loop, the magnitude of the magnetic moment is equation 6-78.
Force and torque on magnetic moment, leading order. The force given by F equals gradient m.b is valid even for time-varying fields. For steady-state fields, gradient cross B vector equals 0, and this expression becomes equation 6-79. The leading order term in the torque is equation 6-80. The potential energy of a magnetic moment in a uniform field is equation 6-81, which follows from F equals gradient m.b.
Macroscopic equations in BC on B and H. Consider the macroscopic magnetization, equation 6-82. This implies an effective current density of equation 6-83. Non-vacuum material satisfies D vector equals epsilon E vector, ecn. 6-84, equation 6-85. Note how E field with leading order monopole contribution has a multiplicative factor, a scalar, geometric, dilation factor, while B field with leading order dipole contribution has an additive factor, a vector contribution. Also note the sign conventions.
Maxwell's macroscopic equations become equations 6-86. The junction conditions become equations 6-87.
Methods of solving boundary value problems in magnetostatics starting with the basic equations. Gradient.B equals 0, gradient cross H equals 4 pi over Cj vector, etc. The general method for solving problems in magnetostatics is to make use of a vector potential or a scalar potential, and in so doing simplify to familiar electrostatic type solutions already known. The most general method is to use a vector potential since gradient.B equals 0 implies SUBSTITUTE times B equals gradient cross A, and with linear media B equals mu H, we get, see the equation shown. Thus, see the equation shown. In Coulomb gauge, gradient.A equals 0, see the equation shown.
If J vector equals 0, however, a magnetic scalar potential can be introduced instead. See the equation shown. For linear response medium we get, see the equation shown, or see the equation shown, in regions where mu is piecewise constant.
In hard ferromagnets, M vector given and J vector equals 0, we can use the scalar potential approach and have an effective magnetic charge density. See the equation shown. Where rho sub m equals negative gradient.m vector is the effective magnetic charge density. Thus, see the equation shown. See the equation shown. See the equation shown.
The general vector potential approach with gradient squared, A, equals negative 4 pi over Cj sub m has equation 6-88. Example 6.5. Consider the magnetic induction at the point P with coordinate x vector produced by an increment of current IDL prime vector at x prime vector given by dB equals I over CDL prime vector times the fraction with numerator x vector minus x prime vector and denominator the absolute value of x vector minus x prime vector cubed, and determine the total magnetic induction when in the presence of a closed loop carrying current I. Solution from dB equals I over CDL prime vector times the fraction with numerator x vector minus x prime vector and denominator the absolute value of x vector minus x prime vector cubed for the magnetic induction at the point P with coordinate x vector produced by an increment of current IDL prime vector at x prime vector, we can show that see the equation shown. This corresponds to a magnetic scalar potential phi sub m equals negative I omega over c.
The line integral for the closed loop is written, see the equation shown, for which we can use the vector relation. The contour integral from C to of dl vector times B vector equals the integral from S to of n times gradient sign with over it times B vector ds to get, see the equation shown. Let's see the equation shown. i.e., omega is the solid angle subtended by the loop at P. Thus, see the equation shown. Where the loop need not be planar.